我不说了，我那个又一个新的那个。那个是我要在都不行，我们给那个是点大概那个是一个大一个。对，然后两个，我们就也在开他没有给他们发的反思。一般子来说我就开始了，哦，所以我就不想。Testing one, yeah.就每次这是个。这里我想当他们的我把你关系了，把你放个反开一点点哦。这个很好，没有什么。然后看。Hey, ready to start? It's just coming. Okay, seems like most of you are coming back from holiday already. Our class is getting very full now. So if you can move forward next time so that people can easily fit in, they come late. Over the weekend, I get a lot of questions from you guys, which is a very good sign, meaning you are studying. Some of you I reply individually. Some of the questions maybe I will address now. Okay. Yeah. So how about let's do some recap. Okay, recap on what we have learned last lecture. Okay, so let's recap on the solvability of linear congruence. Okay, so solvability of linear congruence is really similar to the solvability of linear Diophantine equation. Okay, so the statement is if the GCD AM equals to D, then AX congruence B mod M has a solution if and only if the GCD of AM divide B. Okay, divide the value B that you want to get. Okay, so you can think of this B as the C kind of the C of AX plus BY to C, right? Okay, that C that you want to get. Or maybe I can just change this to C. Why? Because what does it mean by AX congruent C mod M? What does it mean? It means that their difference is divisible by M. Okay, so you can swap it to AX minus C equals to Km for some Kz, or you rearrange again, it's just AX minus Km equals to C. If you like, maybe I can change this M to Y, look more similar to what? Hey, sorry, this M I cannot change, right? Unless I change this to Y. Okay, unless I change this to Y. Okay, so this is very similar to the linear. I mean, not similar, it's actually the same. It's the linear differential equation. Okay, or let's change this K again, maybe change to B. So it's look exactly the same. Okay, does that make sense? Okay, so this mod Y here kind of like remove one of the term from your linear differential equation. Okay, so you go back to chapter 1. Okay, so it's very similar. And moreover, when this D here, this GCD here, divide, now we call it C, right? Divide C, then AX mod C, sorry, AX congruent to mod Y has exactly D solution mod Y. Okay. Yeah, so we have examples for this, right? In particular, this question here. Okay, so we wanted to solve this 12x congruent to 66 mod 39. And we realized that the GCD of 12 and 39 is 3. And so you solve that. You solve this difference here 4x congruent to 9 mod 13. You found that x is congruent to 12 mod 13, and then you convert back to 39. Actually, there are 3 different solutions. Okay. Yeah. So this is the reason why there's a D solution. Okay. So far, so good. Okay, so this is the last exercise we went through. Maybe let's try do one exercise together. Let you do some exercise. Maybe tell me. See, maybe tell me this. Okay, can you solve this based on what we said just now? Can you solve 4x congruent to 7 mod 6? Can you solve this? Based on what we said just now. Huh? You can't? Okay, why? Okay, good. So what's about the 2? How do you get a 2? Okay, the GCD between 4 and 6 is 2, but 2 doesn't divide 7. Okay. So by the previous term, 4x congruent 7 mod 6 has no solution. Okay, so you need to be very quick on understanding this statement here. So this statement here is about if and only if. So meaning one of them is not true, the other is not true. If there's no solution, meaning the GCD won't divide C. If the GCD don't divide C, then the solution, the congruence has no solution. Okay, so it goes both way. So maybe this going both way. Any questions so far? If you don't believe me, try and do your experiment. What do I mean by experiment? So meaning you just go and check it. Okay, go and check by brute force. Okay, so you check it. So in this case here, mod 6, right? So there are like 0, 1, 2, 3, 4, 5, 6 choices. Okay, and then you compute what is the multiple of 4 of them, 0, 4, 8, 12, 16, 20, 24. Do you get 7 or not? Not 6. Okay, it doesn't look right, because all of them are even. Yeah, divisible by an even number. So it's kind of hard to get a remainder 1, I think. Yeah, you can try it out. Okay, it's impossible. Okay, no. Okay, so in this class, right, if you learn how to calculate, it's better than you learn how to check as well. Okay, check your answer. Awesome. All right. Another thing is there's a very interesting question by let me see. Let me check. I find you. Someone emailed me on finding inverse. You want to say who are you? Or maybe I can check who are you. Xiao Rou. Is Xiao Rou here? Xiao Rou, good. Okay. Yeah, Xiao Rou asked a very good question. She tried the tutorial question, so I hope you also tried it out. There's one question looks like this. Uh, so, so basically this question is like, so 103x not 444,999. Okay, so what's your idea on solving this, Xiao Rou? Can I interview you a bit? Find the inverse. Okay, so why do you think that you have to find the inverse first? So if you manage to find the inverse, then you can cancel out the 103, is it, in front of x. Okay. So do you think the inverse exists? You think? You think the inverse exists? If you think that inverse exists, why? Why does the inverse should exist? Because sometimes inverse doesn't exist. When does the inverse exist? GCD of equal to 1. Okay, whose GCD between what? Good. So you need to make sure that. So you need to remember the position. There are 3 numbers to compare here, right? Which 2 are relevant? Okay, you need to take the one in front that you want to invert. Okay, you need to take the number that you want to invert and then comma with the modular and. Okay, so you need to make sure that this GCD of 103 and 999 is 1, and then so that this is a theorem, by the way, so you can check it out. So that 103 inverse of 103 exists. Okay, so we will denote the inverse like this, like what you see in your uh, real number. Okay, 2 times half is 1. Right, 2 times. We don't see it as a half, like we see it as an inverse in this case here. Okay. Yeah. So is it 1? Go back to question. How to check whether this GCD is 1? So there's some ways to do it, right? You want to check whether it's prime or, I mean, at least you need to write down the prime factorization. For example, like 999 is equals to 3 times 333. So okay, so 3 cube, no, 3 square is enough. 3 square times 1 1 like that. So can I split 1 further or not? Sorry, 333 1 1 still divisible by 3. So 9 9 good, very good. So 3 cube times 3 3 3 3 9 3 7. Okay, 37. I think 37 is one of the prime we know. Okay, how about 103? Can we split this? Any prime factorization? 103. If no, how to prove it is a prime? Uh, how to show that it's a prime? What? How many divisor you need to check? Why the prime? Those are smaller than square root of n. Okay, so maybe you can find the nearest square root, perfect numbers here. Sorry. 11, 1 to 1. Okay, so you can check prime below, let's say 11, which is square root 1 to 1. Okay, so you can check whether 11 divide 103 or not. And then what else? 11, 7, 5, 3, 2. Okay, so you check whether they divides 103 or not. If they don't divide, then this is a new prime. Okay, I think it's a prime. Okay, prime. So you can see that they don't have share so there's no common divisor here. Guess all the GCD. So because they don't have common divisor. In particular, P of 10399. Sorry, in particular is 1 because 103 and 999 have no common divisor apart from 1. Or you can use the formula of GCD, right? So it's the PI to the minimum AI BI. Okay, taking product of all this. So you can see there's no common divisor, so that the product reduced to 1. And right, so in this case here, there's an inverse. Okay, so there's an inverse. The question here is how to find this inverse. So here is mod 999, right? So last time in class we mentioned a few methods. One of them is by inspection or you try number, but in this case here, 199 number to try. So, right, crazy. Or what else we can do? Or there's one more way, right? So maybe you take a multiple of 999 and then plus 1, see whether it's divisible by 103 or not. But this number still look pretty big. Alright, so Xiaoro asked if there's a easier way to do this. Okay. Yeah. So if there's an easier way. Maybe I show you something, maybe you can tell me what's the easier way. Okay. So like what I told you before, right? So let's abstract this a bit. So let's go back to this thing here. So your question is, can I put an inverse here? Okay, I put an inverse here. Well, okay, no, so I shouldn't write like this. So instead, I don't want this C, I want a particular C. Can I find an inverse that does this? Okay, your question. Cool. All right. Is that right? Everyone agree or not? Okay. But again, like what we have started just now, right? This linear congruence is equivalent to Diophantine equation. Correct or not? So I can rewrite this as let's say B1 to, let's say, 1 minus. Plus is fine as well, right? Because I can push the minus sign to Z. Okay, to be safe, I don't want to confuse you. So their difference have to be B times 1, right? So if you arrange this, this is the linear Diophantine equation, right? You still remember how to solve this? Huh? What algorithm? Euclidean algorithm. So you can use Euclidean algorithm to find. Or more precisely, what algorithm is that? Extended Euclidean algorithm, because you want to express 1 in the linear combination of A and Y. Okay, does it make sense? So that linear combination will give you this inverse here. This B, the Euclidean algorithm will also give you, right? But then after modding up by Y, this term is irrelevant already. So you just need one of them. Does it make sense? Okay, how about we tried it? Okay, so say also no use, right? We have to prove it to you. Okay, so let's try and do this on this question here. Okay, so now to find the inverse of 103 mod 9, we will express 1 as the linear combination of 103 and 999. Okay, so now we go back to chapter 1 problem. Okay, so what should we do? We should do the Euclidean algorithm. Not that 999 equals to how many times 103 plus a remainder? And someone quickly compute that. 9. 9 times 109 plus how much? 32? 72. Okay. And then we can continue. I think 1 is enough. Plus 31. 72 equals to 2 times 31 plus 10. 31 equals to 3 times 10 plus 1. So you can see that your GCD is 1, right? Okay, from this calculation. Okay, so you can do backward. No? Okay, so using extended Euclidean algorithm. Okay, 1 equals to 31 minus 3 times 10. And then 31 minus 3 times 72 minus 2 times 31. And then 6 plus 7, 7 times 31. And then minus 3 times 32, 7 times 103 minus 72. And then minus 10, 32 plus 7, 9. And then what else? 72. So we replace 72. So 999 minus 9 times 103. 7 times 103. So minus 10 times 999 plus 90. So plus 97. Okay, so maybe you can check your calculator. Is this true? Yeah, check. Do some sanity check here. Okay, so let's say, let's assume this is true. So what do we get? So we get that 1 equals to this big number here. Okay, so let's say you take this linear Diophantine equation here, mod out by 999, what do we get? We get 97 times 103 mod 90, 999. So 97 is one number that multiplied to 103 that get 1. Does that make sense? I hope. That's why this is not a guessing number, not trying out, try and error, but an algorithm to help you. Okay, so there's a reason why you learn a Euclidean algorithm first. So we're going to use it, the previous thing from previous chapter to the next. Okay, any questions so far? Is it clear? Okay. So if you notice, actually on Moodle, right, I also posted up one typeset note. Let me see if I can find it. Yeah, I guess you can have a read. Someone helped me to type my notes. Actually, by my students, she's doing internship, and then I think she found boring. Maybe she come back and read, study my lecture video, and then she typed something out. If you like, you can have a read here. or maybe give some feedback. Yeah. Yeah. So my student was doing an internship. Yeah. Also about internship, right? This morning I just because I was the supervisor for, I mean, academic supervisor for one of my internship students. So we have to meet with their industrial supervisor to get feedback. So I guess it's a very good feedback that the industrial supervisor kind of appreciate our students. Okay. So in what sense they appreciate our students? One thing praised a lot was our student about our students' thinking skill. Okay. So in this university, right, hope that you can develop your thinking skill here. So because I asked the supervisor that what she do, right? She's doing like data analysis, something like that, coding stuff. But then our student is MAT, math student. So you can imagine that half of our I think like studying pure math stuff. I mean theory, proving calculation, stuff like this. But then she appreciate a lot of students that she can pick up tasks really quickly, and then organize data very well. So I asked her a question that if I present you two candidates, one of them is MAT degree, the other one is coding degree or data analyst. I think in your class have CST, right? AIT, yeah, like that, right? So which candidate you prefer? Then she didn't say either one of them, but what she said is you need a quality of thinking skill. Then because in this changing working environment, you need to pick up things very fast. Yeah. Okay, so you can't just I mean there are works to do. I mean there are like boring works to do, but there are more interesting works to do that you need to think somehow. Okay, your boss really like it. Okay, so you need to train yourself. That sense. Okay. Yeah. Right. Yeah. Right. So Max is a very important language. Like I mean, maybe last week I already told you, right? I show you the comment from Elon Musk and Jensen Huang, NVIDIA CEO. I have a student. I mean, I have students in AIT as well. So, for example, in AIT, right, in latest year, maybe we'll deal with language like manifold as well, geometry. Maybe you don't study it, but your frontier knowledge actually build on these languages. So mathematics is very important in this sense. Okay, like CSPR, whatever, you deal with cryptology, right? You can deal with cryptology. These are number theory actually, because like banking system, how they encrypt, decrypt your messages. Okay, so these are the fundamental basic that you're gonna see in this class. Okay. Mm, how about before we continue, any other question? Any other question from last week or assignment? Okay, so for assignments, right, it's due on this Wednesday. If you have any problem, you can approach me. But I cannot, sorry that I cannot check answer for you because if I check for one of you, then should I check for all of you? I don't know. It's unfair, right? So, but tutorial can. Okay, if you do tutorial, you can send to me, have a read. Okay, assignment, the mark is counted, so it's best that actually why student will ask why you need lecture to help you check answer, right? Because I guess we need to be confident in our solution. Okay. And I also will be fair to you. Okay. I won't be biased. Okay. So I will be fair. So we argue based on point, not argue based on preference. Does it make sense? Okay. Because maybe the people you met with is like preference. Teacher like this, I do this. As long as teacher like, I don't care correct or no. Correct. Okay. So we argue based on points. We don't argue based on preference. Okay. So hopefully you will learn this in this class in particular. Okay. Yeah. So in that case, if people are okay, then shall we continue? Okay, so let's continue with Chinese remainder theorem. So a motivation is this problems here. So we want to find a number, okay, that leaves a remainder of 1 when divided by 3, a remainder of 2 when divided by 5, and remainder of 3 when divided by 7. Okay, so in this case here, what you're going to find is something like this. So let x be in z. Yes. Oh, sorry. Thank you very much. So let's x be in z such that the x is congruent to 1 mod 3. So last time I associate divisibility to multiples, right? Now we associate remainder to congruence. Okay, so if two numbers are congruent, that means their difference is divisible by multiple of n, and it also means that their remainder is the same after divisible by n. Okay, so if I translate this into syntax, mathematics syntax here, so this is equivalent of solving, it is actually solving a system of linear congruence. So previously what you have learned was solving one linear congruence. Again, now we want to solve multiple of them together. One variable. Okay. So what's this solution here? Last time I have gave you this spoiler, right? So if you have a bunch of linear system, so what you do is you need to find a solution, okay, in the product of all these. Okay. All right. So what's this answer here? So if you want to prove this kind of statement, right, say there exists a solution, okay, then you need to really find the solution. Okay. I mean, in mathematics, there are two ways. One way is using contradiction. So let's say there's no solution, but then you need to find contradiction. But the easiest one for this kind of existent problem, right? You just produce one solution. Okay, so what's the one solution we're gonna produce here? Well, so I might not prove it to you, but then I'll give you the answer. What's this answer here? So this answer need a bit of construction. It's not too hard. So basically, you start with this product of mi that you need to consider. And then you consider this weird mk here. Okay, so this weird mk here is just taking m. Okay, remove the k, a, k, mk. Okay, so in this case here, you have all the product except mk. Okay, then what's your solution then? Okay, so what your solution looks like? Not yet, actually not yet. Um, let me see. You still need uh, one more criteria here. So basically, find an inverse. Let's call it yk of mk. Okay, maybe I ask you a question. This mk, inverse of mk can exist mod what? Okay, so you need to make sure that this number here, GCD of mk with this thing is 1. Okay, so by this mk construction, right? What is relatively prime to mk? Big mk. Okay, maybe you don't have enough info because you need to realize that we are only solving for these little mi to be pairwisely relative. So pairwisely relatively prime means what? If you pick any two of them, their GCD is 1. Okay. So last time we mentioned about this idea, right? This pairwisely relatively prime will implies that these numbers are mutually relatively prime. Okay, so GCD of everything here is so so you can note that these M1, M2, MK minus 1, MK, which is plus 1. Okay. This is the key here. So this is plus 1. Up to MR here should be relatively prime to little m. Okay. Okay. So you can find an inverse. Then your solution will be built up by these two number with the original solution, which is A1 times M1Y1 plus A2 times M2Y2 plus blah 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 up to MR times MR. Okay. So your solution will be built up by this AI multiply with this special construction here, mi multiplied by with its inverse and then add up all such. Okay, can you see why it works? Maybe you start with mod little m1 here. So let's start with mod with little m1. You left with AI. You left with AI. What happened to this term? For capital M2 up to MR, right? Then you are just removing little m2 out to little mr. So inside here, there are m1, little m1. So you will remove it. But then what happened to this term here? Sorry? There's no m1. But then what does this y1 do? This y1 is the inverse of m1 mod m1. So meaning these two multiply together after modding out by m1, it returns 1. So that's why it returns you a1. So you can apply the same reasoning to all these terms, such that this solution here will solve this system of linear. Does it make sense? Okay. So this term here will reduce to 1 mod little m. And then this term is 0 mod little m. Okay, because here will contain m1, m3, and then blah 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 blah. Little. Okay. Does it make sense? Is it a question? Any question? Yes? Okay, good. Yeah. Okay. So kind of level here. Okay, should we try an example? Okay, let's try an example. Okay. So solve this system of linear congruence. So for this Chinese remainder theorem to work, right? We need to make sure that this modulo n are pairwisely relatively prime. Okay, so you need to check what's the GCD of 4, 5, what's the GCD of 4, 7, and then what's the GCD of 5, 7. So what are they? They are 1. Okay, so these numbers are pairwisely relatively prime. So by Chinese remainder theorem, let's call it CRT here, it has a unique solution mod the product of these numbers. Okay, so which is 4 times 5 times 7, 140. Okay, so the first step is you need to set up this capital MI here. Okay, so MR. So in this case here, there are three product of three numbers, right? So there are M1, M2, and M3. Okay, so for M1 here, capital M1, you need to take the products of them divided by little m1, so which is 4. And then the other one, you take away m2, little m2, which is 5. And then for the third one, you take away little m3. Okay, so you get 35, 28, and 20. Okay, so what's the next step? You want to find the inverse. Okay, so now you're gonna solve the inverse. So first of it is 35 times y1 is mod little m1. So little m1 is 4 here. Okay, so I hope you can remember this position. And make sure you don't simply maybe divide. Otherwise, we'll get you wrong answer. And then 35 come from the first thing. 35, yeah, 35 come from here. So the next one is the similar. So you want to find the inverse of 28 mod 5. And then the last one, you want to find the inverse of 20 mod 7. Okay, can you solve this for me? Find the inverse. Can I solve this? Tell me what is y1, y2, y3. Anyone found it? Hmm? Anyone found it? Oh, yeah. Sorry? Y1 is what? 9. 9? You sure? 3. 3 or 9? 3? I also got 3. Well, I mean, like, because 35 is still relatively big, right? So you can reduce it. So you can reduce to 3 times y1 mod 1 congruent to 1 mod 4. How about y2? 2. Okay. Y3? Huh? Y3? Sorry? Y3. Maybe I reduce a bit. 6. Y3 mod 1 and y3 mod congruent to 1. Huh? 6? 6. Okay. 6, 6, 36. 36 is 1 mod 7 because 7 times 5 is 35. Okay, so the difference is 1. Okay, so what's the solution then? So how we assemble this solution? Okay, so the solution formula is x equals to a1, okay, times m1, capital M1, okay, times little y1, so the inverse. And then you do the similar thing to all the other terms and then add them up. Okay, so you need to pick out what is a1 here. So a1 here is 3, and then a2 is 4, a3 is 6, okay, and then capital M1 is 35, and then capital M2 is 28, capital M3 is 20, and then put back your inverse. So these are modulo because these are modulo mod 140, right? So these are up to modulo. So this big number, what's this big number here? Maybe someone can compute it. Huh? 1259. Okay, 1259. Okay, good. So can we further reduce a bit? Maybe 139. And you can start and do your sanity check. Put back your number. Does it solve the system of linear complex? Okay. So this 1259, right? What number you want to pick here? Sometimes depend on reality. Okay, sometimes depends on reality. Because sometimes they give you a range to this number. For example, I gave you the uh, analogy of the Chinese emperor going to war, right? So they have troops, right? So they have troops, then they arrange into these linear congruence. Okay, maybe arrange to different way of marching. Okay? And then they know that they are roughly around maybe 1,000 and 1,300 troops. Okay, so for this solution to make sense, you will pick this number instead of 120. Okay, because your solution is just throughout to modulus. Okay, so it depends on what number makes sense to your question. But this question is very general, so any solution will work. Okay. How about you want one more exercise on this? Okay, so I let you solve this. Okay, from scratch. Try and solve this, and then we'll check answer together. I give you maybe 3 minutes. You can try and discuss with your friends. Talk to your friends beside you, behind you, in front of you. Introduce yourself. Hello. Okay. So again, these linear congruents are modular 4, 5, 7. So 4, 5, 7 are pairwisely prime. So by Chinese remainder theorem, you have a unique solution. Mod 140. Basically, the previous calculation is the same, right? M1, M2, M3 in this case. Is it the same? Yes, exactly the same. So first step, you go and find what's your capital M1, capital M2, capital M3. And then again, you find what's the inverses. Okay, mod little mi. Okay. And then 3, 2, 6. Okay, so what's the solution? What's the final solution people get? What's your final solution? Huh? 60? 66. Okay, 66. Yeah. Okay, hopefully you get 66. Maybe you get 626 from this formula first, and then you get 66. Mod 100. Okay, note that this solution is always a modulo sign. Is it? Yeah, this solution here is a modulo sign. So it's a mod of this capital M here, product of little m. Okay, so far so good. Actually, there's one question that you also can solve. For example, how to solve this? Solve 17x modulo 9 mod 276. Okay, maybe one way to solve it is like what we did at the start, right? You go and find or GCD of 17 and 76 is 1. So the inverse of 17 will exist. Okay, then you solve it like that. But then you actually also could realize that 276 is actually 3 times 4 times 23. Okay, 2 times 4 times 23. In this sense, um, in this sense, maybe you can multiply inverses to 17 first. Let's say okay, what this number here. You realize that you can use Chinese remainder theorem here because you want to find a solution mod of product of pairwisely relatively prime. So meaning what? This is equivalent of solving x mod 17 inverse 9 mod 3 and then x congruent to 17 inverse times 9 mod 4 x congruent to 17 inverse times 9 mod 23. Okay, so meaning what? You can use the formula of Chinese remainder theorem to solve this. Okay. Because previously you need the capital MI, right? So there's one of it. It's not enough. But then here you got 3 of them. Okay, so you can use the formula to solve it. Okay, or not? Okay, so you can compare the two methods. Okay, which one is easier? Okay, sometimes one is easier than the other. Okay, or you can straight away solve this. Okay, like what we did at the start of this lecture, right? Go and find what's the 17 inverse, and then you reduce it. Or you use the Chinese remainder theorem to help you. Does it make sense? Okay. Okay. Yeah, any question before we proceed? Yes. You can continue and go back and compute this. I'll give you a solution. You can check answer. Any question before we take a break on Chinese remainder theorem? Okay, if no question, we will break until 11:04. Okay, 11:04. OK，耶，嗯，
他们俩之间有公数，他们俩之间也有 factor。但我可能去就解这个，能找他们的。
哦，没有喂，如果有 common divisor，你应该是找不到 inverse 的，你只能够用，我想看哦，你要用有一个 theorem 嘛，对这个 theorem，对，你要用这个 theorem 才能够把那个 c 去掉啊，对，对，喂，是吗？你在问这个问题吗？谁跟谁有 common divisor？
他们 common divisor 是30，
啊
，common
，OK，
divisor 是111。就是我的意思是说，
嗯
如果他们的
嗯，
common divisor
不是
不一样的话，
不一样。
对，
喂，不是，就是来，OK，这个东西有解，什么时候有解？你要去 check 这个 GCD 哦，这两个这两个 GCD 要 divide 这个东西才有解，如果没有解，你就不用解它，明白吧？
他们俩的 common divisor，
对，不，它的 GCD 不只是 common divisor，它的 GCD greatest common，它一定要 divide C 了过后才会有解，没有解你就不用解它
他们两个 divisor，他的
，greatest
GCD
呀，
要能除以他们的
没
divisor。
有错，如果不能 divide 就不用解它，解不。
哦，那我后面应该怎么做呢？
什么意思？什么意思？
就是
就是解不了，no solution，no
嗯
solution，解不了就 no solution。
嗯
313解得了313，
嗯，
919313334，哎，解得了啊，解得了啊，这个可以被删除啊，所以这个你要用这个来解啊，这个对吗？
还有刚刚最后讲的那个，休息前讲的那个，
下面好休息前，这个
这个的话，
嗯嗯，
那 x 不是零，
为什么呢？
它 module 3不是零吗？它不是有9吗？
你给我想想看啊，是这个是，对啊，第一个是零，没问题
哦，我懂了。
没有问题，
好的好的。
没有
讲那个 assignment
什么
怎么比较，就是可以在那个平板上写，然后这样子。
没错，
我还没有没想过拍照，
打印上不用也不用拍照可以，
我不像
如果写在纸上就要拍照。嗨，hello，
当时他这个就是我没听懂，就是为什么？他意思就是说把这两个长短，就是翻成短，然后成拼了一个模，
对，
然后就对他就是求语数的一个变化。
你的答案会活在这一个模里面，
就是等于
就是说，你看这个答案，它是66模140，所以说你140加66还可以解这个，还可以解完全这个，对不对？懂什么意思？就是说，就是说，哇，140加666也可以解这三个，不只是666，就是66加140的倍数都可以解掉这个
就相当于就是说，这个最新的就我们新的出来的大看就是大写的，它就是相当于是这几个质 bring 的一个公倍数，所以就是那个
他们 multiple。
yeah，
不一定，它可能会跟倍数可能会比这个号码小，
哦，不是它就是其中的什么
什么意思？
就是
其中一个 multiple 对，其中一个 common multiple，其中一个对，是的。 For those who are here, I'll take attendance first. For 苏月，is for 苏月 here? Okay. 施杰生、潘家豪、李承炫，yes. 周红婷、朱祥哲。Rumbo is Rumbo here. 一航，陈一航。Okay. 唐思怡 ，I think is sick. 刘真贤、姜通俊、叶伟通、陈子涵、王金珍、金珍 ，OK。彭一佳，yes。陈子、胡崇瑞、陈思曼，yeah。嘉诚、冰珍，OK。浩源、OK。浩然呢？OK。彭欣怡、田文琪、张小柔、张泽瑞、陈凯莹是吗？凯莹 ，Tiffany， OK。Check it。Jasmine， yeah， 然后林佳静，梁家月 ，OK。卢泽新，韦明涛、杨旭成，sorry，曾义飞、陈玉清、李林义，林义 here， 李林义。曹化元、王雅 here， no here。李浩聪、刘艺书、潘子良。Hey, hello. You just came back? Okay. 甘金浩、侯明炫、李威汉。Okay. 林毅是Ayub Saudi Ayub。Joy Lee， 何明浩、黄棋子、秦子祥一直，小熊培成、张馨予、周瑞敏、赖文义、陈子呢？OK。陈子睿、李小环、曾天健、新 Aaron Febrin， 孙瑞全、Isaac 西宾克 at the back， OK。高硕，Hey, you're not here on Friday? Friday not here. Sick. I don't think I don't. 王思涵、王思怡 ，OK。车明宪，车是什么姓？曹的曹。Okay, I will continue taking attendance later. If you didn't If you realize that I didn't call your name, please come up after the lecture. Anyone is a new guy here? Completely new. What's your name? Huh? Saluting? Sorry? Chaldin. Chaldin. Okay. Nice to meet you. Where are you from? India? Okay. Are you in Moodle yet? Are you in? No, don't know. I think I added you in. Yeah. Have you found it? Yes. Okay. Good. Okay. So you just arrived? I see. When? 2 days ago. Okay. Okay. Hope you have a nice semester here. Okay. Okay. Okay, good. Let's continue. So now we will have a more complicated system, which is a system of linear congruence in two variables. Okay, previously we just have x, right? Now we're gonna have y. Okay, it's really similar to your linear algebra now. Okay, so you can think of it as a soup up version of your linear algebra, but we are not dealing with real numbers, instead just do integers. Okay. So let's play a bit. Let's do some motivation here, motivation examples here. So let's play around with this motivation. So let's play around with this system of linear congruence in two variables. Okay. All right. So what do you do in linear algebra? Eliminate one of the variables, right? Okay, maybe we can do similar stuff here. So what can we do? Maybe I name the first one as equation 1, second one as equation 2. So I multiply 1 by 5 such that I get 15x plus 20y congruence to 25 mod 13. Then we call it the equation 3. And then the second one I multiply by 4 to get 8x plus 20y congruence to 28 mod 13. Then we call this equation 4. And then I realized that they are the same terms here. At the same time, they are mod. The mod n is the same, so that I can do this. Otherwise, maybe there's something wrong there. So maybe I take 3 minus 4, such that I get 7x congruence to minus 3 mod 13. And then 7 and 3 are prime. So the inverse as this, I guess it's easy to see, right? What's the inverse of 7 mod 13? 2. Okay, 2 times 7, 14. 14 is 1 mod 13. So I multiply by 2 on both sides, such that I get -6, which is 7 mod 13. Okay. Then I plug this x into my equation, right? Either one, either number 1 or number 2, up to you. So what do I do? Sub, maybe sub number 5 into number 2. Okay, so I get 14x, sorry, no more x. 14 plus 5y congruence to 7, which is 5y congruence to -7, or 13. And again, you found that the inverse of 5 mod 13 is 8. Okay, and then -7 is 6. Okay, so we get 6. 6 mod 13, I mean 6 times 8, which is 48, which is 9 mod 13. Okay, so you can do some sanity check. Check whether is it 3, is it x mod 7 and y mod 9 will solve the equation. You know how to check? So you just put your x and y back to your equation 1 and 2. Check them. Okay, see whether you get 5 and 7. Okay, does it make sense? Okay, so what I want to present to you is very similar to what you do in your high school and linear algebra. Okay, so similar to what we wanted to know before is, can I straight away look at the system and then tell you whether there's a solution or not? Okay, if there is, can I straight away tell you how to find it or not? Okay, instead of going through all this substitution, whatever. Okay, so the solution is positive. Okay, so meaning we have a formula for it. Okay, instead of going through these substitution business here. So basically is you are given a system of linear congruence here. So mind you about these coefficients for A, B, C, and D. And then we will form this delta here. Maybe we call it a discriminant. Okay. Let's say this discriminant here have GCD 1 with M. Then you have a unique solution modulo M. Okay. And then I give you how to find this solution. So there's a, instead of discriminant, right, there's a discriminant bar here. What is it doing? What's this discriminant bar? So this discriminant bar here is, you need to find this bar as the inverse of the discriminant of. Okay, because the GCD of this discriminant and M is 1, right? So there's an inverse. And then you have to take this inverse multiply by this DE minus BF. What's DE minus BF? DE minus BF. DE minus BF. Let me try and work this out. What's this DE minus BF business here? So DE BF. Okay. So, and then this one, oh, maybe I will tell you why I arranged like this later. So what is AF? AF minus CE. AF minus CE. Okay, C is at the bottom. Okay, good. So why I arrange like this is because, well, if you learn linear algebra before, right, solving system of linear equation is equivalent to solving the matrix. Okay, so we can rewrite this as something like this. A, B, C, D. No, E, F, G. Just E and F. Okay, so this discriminant here is actually the determinant of this matrix here. You guys know determinant of a matrix? AD minus BC. Okay, good. But then you take this inverse, multiply by another determinant. Okay, so what's the matrix you're looking at? So this matrix, you kind of looking at B, D, E, E, F. But not quite B, D, E, F, right? Because this determinant here should be, if you look at this determinant here, so meaning you kind of like take this part as your matrix. Okay, so this is BF minus ED. So meaning what? There's a minus sign in front of this. Okay, but for the second one, it's just a determinant of AC and EF. AF minus EC. Okay, so this is the second one. AC. How should I draw it? Can I draw like this? Okay. If you want to remember this formula like that, maybe it's easier. So far, so good. Okay. I guess we won't prove it to you. I guess I prove it in the notes. Maybe we can test this. Okay, test this with the question we had just now. Okay, test this formula. Okay. I mean, before even, so the thought process of mathematics is, even before you prove it, right? Definitely you need to make sure that it works for the examples you have. Right or not? And then you conjecture that, oh, this is true. And then you prove that it's always true. Okay, so you have to convince yourself first, okay, this theorem is working. Otherwise, don't bother proving it. No need. You convince yourself it's true first, and then you start proving. Okay, so let's try this formula using this question. Okay, see whether we get the same answer or not. 7 and 9, right? Okay, remember this 7 and 9, let's see whether we get this. Okay, so let's check it. Where's my card? All right, so okay. Never mind. In that case, we just copy. So what's this question? 3x plus 4y congruent to 5 mod 13, and then 2x plus 5y congruent to 7 mod 13. Okay, so let's start with this determinant business here. So our AD minus BC will be 3 times 5 minus 4 times 2, which is 15 minus 8, which is 7. So now the question is, did you see that the GCD of 7 and 13 is 1? Okay, kind of obvious. Two different primes. Then we will straight away find the solution here. But to find the solution here, okay, D, E, B, F, A, F, C, E are given already. What you need to figure out is the inverse. Okay, so we're going to find delta bar inverse such that delta bar times 7 equal to 1 mod 13. What is it? 2. Good, very good. So delta bar is 2. Okay, then we use this formula. X is equivalent to 2 times what's DE here. So remember the position, the relative position is kind of important here. So 5 times 5 minus what's BF? 4 times 7. Okay, mod, this is mod 13. And then the other one, Y equivalent to 2 times AF. So 3 times 7 minus C. Where's C? I think it's the bottom, right? 2 times 5. Good. All right, so compute this. 25 minus 28, which is 23, which is minus 6, which is 7, not 13. The other one, 21 minus 10, which is 11, times 2 is 22. 22 mod 13 is 9. Okay, so do we get the same answer? Yeah, we get the same answer. Yeah. So, yeah, I think that's it. Yeah. Okay, so this formula will give you the solution as well. Okay, so if you are interested how we figure out this formula, you can look at the proof. Okay. Or actually, you can do a sanity check here. Okay, maybe to help you understand why it is true for general. Okay, why this delta bar matters. Okay, you can substitute back and then see how they cancel out. Okay, to give you E and F. Then you will see why it works. Does that make sense? Okay. Okay. How about should we practice more on this? Should we practice more on this? No? Good. Can skip. Anyone want to practice more? Or you guys can skip this question. Huh? Homework. Left and homework. Okay. Very trivial. Okay, good. I like you, I know. Yeah, I like this kind of student. Very independent. Okay. But maybe look at this. How about look at this? Okay. Let's not practice calculating, but then look at this. Can you solve this or not? Can you solve this? If you just follow the way that the delta, figuring out the delta, right? Okay. So what's this delta here? AD minus VC, right? Sorry? Minus 3, huh? Minus 3, is it? Wait, let me check. So 1 times 1. Oh, okay, yeah, sure. Okay, minus 3. Yo, minus 3. Then -3 and -7. Wait, let me see. I picked the wrong question or not. Sorry, I picked the wrong question. Let's change to this question. This one. Yeah, this guy. Okay, try this one. So if you find the delta is 4 times 1 minus 3 times 3, which is -5. How? The GCD of delta and 5 is what? 5. It's not 1 anymore. So you cannot use the theorem. Okay? You cannot use the theorem. Then you need to solve like what we did previously. Okay? So try and eliminate variables. Okay, so what can you do here? Times 4? Which one times 4? First one times 4. Is it useful if you multiply first one times 4? So what do you get? 4x plus 12y minus 4. Then 7 times 3. Okay. I see your way. So 9x plus 12y equals to 6. Then what do you do next? Take their difference. Okay, so which one you want to minus which? Maybe call this number 3, call this number 4. 4 minus 3 perhaps. So you get 5x congruence to 2 mod 5. Okay, but what's this? um, yeah, sure. So what's this? 0 equals to 2. Is it possible? No, right. Okay, so this is a contradiction, which is absurd. Okay, so no solution. Absurd is like crazy. Stupid. Actually, you can just multiply 1 by 3 also is enough, right? So that you get 3x on both sides. You can just multiply multiply the first equation by 3. Okay, then you can eliminate 3x as well. Okay. Does it make sense? Okay, so don't just remember, again, I want to remind you, don't just remember formula. You need to also remember when the formula will work. Okay, it's very important. This is like like a key. Okay, like a key. Do you play games? Play games? So you need to hit certain requirement, only then you can use the power. Right? Okay, so this is like what it means. Yeah. So this theorem works when you have this GCD of delta M2. Okay, otherwise you cannot use this power. Okay, this power is not available for you. Okay, good. Let's see. Yes. Oh yeah, sure. Okay, so someone mentioned about Cramer's rule. So you can think of this like a Cramer's rule. Yes, that's right. Okay. So Cramer's rule. What does Cramer's rule do? It tells you when the matrix have the inverse, right? And so you can think of it like you're taking the inverse of A, B, C, D, put it together. Does it make sense? So it kind of like provide the inverse of this matrix here. Yeah. Okay. Yes. This is looks similar to Cramer's rule. For those who learn linear algebra before, okay, you will relate this. Okay, you can try and go back and compare Cramer's rule and this formula. Okay, very similar. Yep. Okay, in this case, let's go to the next part on divisibility. Okay, so these are the divisibility tests. So it tells you when is a number divisible by another number. Let's say I give you a random number here, 3, 4, 5, 6, 7. So this is a motivating example here. When is it is this number divisible by 2 or 3 or 5 or 9 or 11? Okay, how do you decide? Maybe 2 is easier, right? Only when it's even. Yeah. If you have 2 as your factor, it should be even, right? Yeah, but this is odd. But in general, how do you figure out this in general? Let's say you don't have calculator. Can you still do it? Okay, so yeah. So one decomposition is very important, okay, to see this without doing calculator, without using calculator. So note that you can write 3, 4, 5, 6, 7, right, as a sum of 3 times 10 to the 4 plus 4 times 10 to the 3 plus 5 times 10 to the 2, okay, plus 6 times 10 plus 7. Okay, I claim that this is easier to compute. Right? Because we can use congruence. Okay, we can use congruence because we can just check how does this 10 reduce congruence 2, 3, 5, 9, 11 first. Does it make sense? Okay, so for example, why is this congruent mod 2? Okay, we don't need to look at 3, 4, 5, 6, 7 yet, right? We can just process for 10. Okay, and then we can realize that the first 4 terms will disappear because 10 mod 0, 10 congruence to 0 mod 2. Okay, then you're left with 7 mod 2. Okay, maybe I write a reason here because 10 to the any power n is 0 mod 2 if n is greater than 1. Okay, but then 7 mod 2 is 1 mod 2. It's not divisible. Why? Because 1 mod 2 is not divisible. Right. To be divisible, you need to get 0. Okay, the remainder is 0. So how about 3? Is it easy to solve? There's a reason why we pick this number 3, 5, 9, 11. So what if 3? What if we consider mod 3? 10 will reduce to 1 mod 3. 100 will reduce to 1 mod 3. 1000 will reduce to 1 mod 3. Okay, so all these power to 10 will just reduce to 1. So because, so let me write here. So because 10 to the n modulo 1 plus 3. Okay, so then what do we do next? We just simply process for the rest. I guess it's easier. It's easy to see, right? So here is 0 plus 1 plus 2 plus 0 plus 1. So you just left with 1 mod 3. Again, not divisible by 3. Okay, you can use your calculator to check whether it's the same or not. How about 5? 10, power of 10 obviously is divisible by 5. Okay, except number 1. Okay, so you get modulo 7 mod 5, which is 2 mod 5. Okay, so because 10 to the n is congruent to 0 mod 5 for all n greater than 1. Okay, so for those who just come, this sign is saying for any. So this is an inverted capital A here for any. We try 5, we try, how about 9? How about 9? What is 10 mod 9? 1. 100 mod 9? 1. Okay, so you can check that. Actually, it get the same calculation as mod 3. Okay, it's the same calculation here. So up to here is the same. Okay, up to here is the same. But then the next step should be different. Okay, so the next step you should get 7 mod 9. Okay, because it's a different mod to your single digit number here. How about 11? How does 11 react to power of 10? What do you think? Huh? Similar? Similar to which one? 3 or 9? Not quite. Not quite. Okay. So instead of figuring out the powers, right, we really just need to know what happens to 10. Right or not? Because this power is just, let's say, 10 to the 4 is just multiplying 10 4 times. Right or not? Okay. So we just really know what happens to 10 is enough. Okay. What does 10 mod n do is enough already. So for example, let's do the 11 one. Okay, so note that 10 is just minus 1 mod 11. So I can replace this 10 right by minus 1. So you can see that depends on the power, either the minus 1 will survive or either it will become positive. Okay, so when is it positive? When is it negative? When you have a even power, it will be positive. When you have an odd power, you will have a negative. Okay. So in the end, what do you get? You will get an alternating sign here. Okay, so you get 3 minus 4 plus 5 minus 6 plus 7. Does it make sense? Okay, so depend on how many 10 you want. In other words, the power. Okay, then this reduced to what? Again, I think this is not divisible. This is 5 mod 11. Okay, can see it? So something I want you to observe here. What do you want to observe here? If it is mod 2, what number is significant here? The last digit is significant. Whatever happened before is not important. This also matches up with our intuition, right? Only even number is divisible by 2. So even number, how do you see even? Do you care about the first few digits? No, you just only care about the last digit, whether it's 2, 4, 6, 8. And then to check for mod 3 or mod 9, what do? You only care about every digit, the sum of every digit. You only care about sum of every digit. Not the calculator. Sum of every digit becomes very small. Okay. And then mod 5, mod 5 is similar to mod 2. You only care about last digit, correct or not? Is this what? I mean, you look at the column of multiplication table. 5 times 1 is 5. 5 times 2 is 10. Either 50, 50, 50 appearing at the top. And then for mod 11, okay? So mod 11 is a bit different from mod 3 and mod 9. Instead of adding up the digit, what do? You take alternating sign. Okay, so how do you take alternating sign? You put a plus at the even power of 10. You put a minus at the odd power of 10. Does it make sense? Is it correct? Yeah. So 7, what's the power of 10? 10 to the 0. Okay, 0 is even, so it's a plus. And then 60, so minus. 500 plus 4,000 minus. Okay, plus, minus, plus, minus. Okay. So I use this example to prove to you already. Basically, we'll go through this thing again. So the key point here is this. Okay, this is a very key point here. Okay, how to split out your number. Okay, split out as a sum of in hundreds, thousand, 10,000, and so in power of 10. Okay, and then interpret how this can react under different mode. Make sense? Okay, so basically, let's go through the statement again. So an integer is divisible by 2 if and only if its last digit is even. So there are two directions going on here. Yeah, if and only. Okay, you just need to check the last digit is even or not. And if you want to check whether it's divisible by 5, you also check only last digit, whether it's 0 or 5. Okay. And then if it is divisible by 3, you just need to check the sum of digit is divisible by 3. Okay, you don't, so this provide a very convenient way is you don't need to do the division algorithm on your big integer here. You just split your integer into sum. Okay, for example, like that. Okay. Yeah. Okay. Do you believe that this will simplify your method of checking? Do you believe? Do you believe or not? Like let's say I give you 1,000,000. Let's say 5, 6, 7, 8, 9, 8, 9. Okay, maybe you say you want to use calculator. I say you don't need to use calculator. But instead, what do? Instead of considering this, consider this. Correct or not? But then you realize that, oh, maybe this number is still big as well. Let's say this, I don't know is correct or not. I simply put a number here. Let's say you want to figure out this. Do it again. Yeah, do it again. Do it again. Do it again. Do until the stage that you can use your hand to calculate. Does it make sense? Yeah, no? Yeah, so this will simplify your calculation. Okay. Yeah, so how about try this? Try this 2 questions. Yeah, I give you maybe 4 minutes. Try. Okay. So I don't have answer with me. So maybe you should tell me which one is divisible by 3. Is A divisible by 3? No. Okay. How about B? Yes. Everyone got the same? The same? Okay. So how many times you do summation of a digit? Is it once is enough? Is once enough? Huh? Is once is enough? Maybe you combine with doing your congruence method, right? Maybe you already simplified it very quick. So what do you get before you decide? What's the number you get? Maybe we can check if all of us get the same answer. 1. 1? I mean, there are only 3 choices, right? 0, 1, 2. Okay, so it's 1 maybe. How about the second one? Huh? Sorry? Nothing. Okay. Everyone should get this. Okay, hopefully everyone got this. If not, please check again. Okay. Next, an integer is divisible by 9 if the sum of the digit is divisible by 9. Okay, so this is very similar to mod 3. So another bunch of number gave you. Do you want to do this? Or you want to do it yourself? How about the rest? Cannot everyone's front one say yes. How about the back? You want to do together? Or you okay with doing yourself and then check solution later? Sorry? It's okay? Okay, skip this. Okay. Next. An integer is divisible by 11 if the integer formed by alternating adding and subtracting the digit is divisible by 11. Do we have example of this? Okay, maybe let's try this. See you are careful enough or not. Figuring out this question. Okay, maybe give you 4 minutes. Try do this. Yeah, so they are like how many plus minus you need to take care. Like 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So which one is divisible by 11? Which one is not? Huh? B. B, yes. A, no. Okay. Everyone got the same? Okay. Okay. Do you have answer before getting no, yes? What's the A you get? 8, huh? Okay. 8 mod 11. And then yes, 0. Okay. If you tell me 2, then there's something wrong. Okay, good. Okay. I'll write out solution and then maybe you can check again later. So before we go to Fermat little theorem, I want to mention another application. Maybe people will ask, study this for what? Study this for what? Okay, tell you for what. Okay, so do you play sports? Any sports you play? No, no sports. E-sports 王者荣耀. 王者荣耀. Honors of King. League of Legends. Dota. Or do you play basketball? Volleyball? Volleyball? Swimming? Okay, good. Swimming, good, good. Sleeping. Someone says sleeping. Wow, we got resonance from different peoples. So this congruence, right, is applicable for doing a round robin tournaments. You know what's a round robin tournaments? So you play in a groups, play among the group first, and then you pick maybe the first or second, and then you continue with your what do you call that? Yeah, round robin is sell to side, but after that, what you do was like pair up and then fight for the final, semi-final, and so on. So you can use congruence to do this round robin tournaments to schedule a tournament for, let's say, n teams, and every teams play at most one match per section, and the tournament will last for n-1 section, so that each team will play every other teams exactly once. This is very important. Okay, so that otherwise, if people play more than others, they will complain, right? Hey, why that team I play only once, I play twice, and wasted my energy or something like that. Okay, so you need to make sure the fairness here. Okay, so how do you do that? So this method we're gonna tell you is it will work as long as you have n even teams. But this is not true in general, right? Maybe in real life, there's you open for 8 position, only 7 pairs come. Okay, only 7 pairs come. But we're gonna give you a solution such that it will work for as long as n is even. So how do you make up the extra one? Okay, we call it a phantom or dummy team, the starting. Okay, so maybe if you look at, for example, badminton, or swimming, or if you watch Olympics, okay, if you watch at the schedule, sometimes you will see bye. Okay, so meaning that's the phantom, that's the dummy team. No one will fight him for that match. Okay, so then what do you do? Actually, very easy procedure here. So for n teams, right, you label 1 to n, and then for I and j not equal to n, meaning the last guy, and I and j are different. And moreover, I plus j is modulo k mod n minus 1. Let them play at the kth round. Okay, let them play at the kth round. So I and j will add up, and then when it is equal to k, let them play at the kth round. Okay, so then we are left with the NO because the last team we are not setting them yet. And another team is called the I team, such that I equals to k mod n minus 1. Then you pair them together. Okay, so this method will make sure that everyone plays exactly once in that team. Okay, so there's a proof, but this is the procedure. So next time you join badminton club, you want to do round robin, apply number theorem. Okay. Yeah. Okay, so we even have this calculation for you. You can go and verify it. So for example, let's say you have n equals to 6 in this case here. Okay. So the by here meaning it play the number 3. Okay. The by here will mean that it play with the 6th team, but the 6th team is nothing. So everyone got a 1 by. Okay. And play with other team at least once. Cool. So instead of manually arrange, okay, you can use this formula to calculate. All right, no? Obviously, you can manually arrange, but it's, let's say you got 64 teams. Okay, so we got this formula to help you to work out. So I think this is pretty practical. So I put this in. I don't know. Actually, it's in your textbook, actually. Yeah, so I found this is very interesting, so I added it in. In your textbook, there's some other application. I encourage you to read about it. Okay. Any questions so far on application? Okay, so I let you see the divisibility, and then I let you see this competition application. Okay, so question? Any question? No question? Questions? No. Yeah, some of you found some mistake in my lecture notes, right? So I updated some of the parts. So make sure you always download the latest one, because sometimes I did calculation error. And if you are not sure about your steps, right, you can ask as well. Okay. Yeah. So in this case, let's break. Let's break until 12:05.没有，就有点像你考试的时候，就是一写下来，
就是拿平板还是纸写都行，那个 PDF 就
不是这边，可是要
PDF
确保它清楚，它
这个是
写下你的名字，就在 ID 点。Hey, yes.
Is it we need to submit together with the question?
You could.
Could.
You could.
And if I write with my tablet, is it acceptable?
Yeah, sure. Make sure it's clear, and then which
You
question.
mean is
Yeah. Then your name. Yeah. Okay.
Yeah, where is it?
Yes.
Cameras rule?
Kramer's rule.
Yeah, cameras rule. That seems like it's really. I just
This one.
yeah.
Hmm.
I think if you use cameras rules here, and you will get this.
Oh yeah, sure.
Yeah, that's the same.
So it's the same, is it?
So,
Okay.
so it will not work.
Sorry, say again. Will not work.
So if if there's not less,
Okay.
and but you use cameras rule and and you use this,
Uh-huh.
and it's wrong.
It's wrong. Yeah,
Yeah,
sure.
yeah.
Yeah.
So it's
Previous rule also need this, right? Because you need
Yeah,
it
yeah.
to be. I mean, like,
Uh,
okay, premise rule, I guess. Wait, what's the premise rule condition? You need the matrix to be invertible, right?
yeah.
Yeah. But then here is a bit. Wait, let me think. Oh yeah, invertible, but this will imply that this determinant is not one. So if it is not one, then okay. So Cramer's rule want the matrix to be invertible, correct? But then this will imply that the matrix is invertible because this delta is having a inverse, so it's not one. I mean, it's not zero.
Mm.
Doesn't make sense. Yeah, so this Cramer's rule. I mean the formula. Just take a look. Yeah, Cramer's rule need the determinant to be non-zero, right? And then
Yeah.
this will implies that this determinant is non-zero.
Yeah.
Yeah.
So that's the same.
It's the same.
Yeah.
But this one, this formula, is it the same? A bit different, right? Imply.
Yeah,
Oh,
yeah, you use this.
yeah, because this
Yeah.
is the inverse.
Yeah,
Oh, yeah,
it's
sure.
inverse,
Yeah, sure. Okay. Similar.
Yeah.
tháng 7 rồi hiện tại mình là cao đúng sự ao ăn谢谢你，谢谢，感激啊，感激啊，谢谢。这个哦，下次自助餐我们也是，我们去吃自助餐。OK，还有这个，VIP 什么？大概去一个什么地方？按照公寓去，然后去组织上市。我有团队，我有团队，这团队。买个，要去，yes.
Okay, last few be attendance, 双峰 yeah, 心灵 okay, 嘉凯 okay, 卓娜家福冲布王冲布 okay, 吴毅崔文倩汉旭 okay, 兰坤嘉怡赵泽宇一收四收尸一收四
陈少涵。Okay. Are you just back? You just back to campus? Okay. 陈卓、李乐山、彭奕晨、赵星辰、诺耶、玉涵、黄玉涵、彭玉兴。Yes.
我们的假期是要回来的，我们的假期。在那个 MP 时代，所以然后现在 A 就是我的假期啊。对，我 writing 像 writing 那个考考，像我现在 writing 我开始到我以前那边开始我买还有马来西亚每次买然后对呀，他们都想买的。我都看看那个。我就别说了。比较对，对呀。慢性热啊，也得。但是但是它是两回事。
Hello. Okay. Let's continue. Next we will learn Fermat's Litter theorem. So this is called Litter theorem. So meaning there are other theorem. Other famous theorem about Fermat is called the Fermat-Last theorem. Fermat-Last theorem was a long conjecture. Yeah. So what's about last theorem? Maybe talk about last theorem before we talk about Litter theorem. Litter theorem is easy to see or prove. But last theorem will be something that you would know. It is, let's say, if we want to solve for xn plus yn equal to zn, is this linear, not linear congruence, but linear differential equation here has integer solution for all positive n? Okay. Well, I think one kind of linear differential equation in this form you are very familiar with is Pythagoras theorem. a squared plus b squared equals c squared. This definitely have integer solution, right? They are Pythagorean triple. These are the famous Pythagorean triple. For example, what? 3, 4, and 5, is it? 3 squared plus 4 squared equals to 5 squared. Okay. So you would naturally ask, if I increase this power here, does integer solution exist or not? Okay. It turns out that no. Okay. And then this create a very big branch of mathematics, okay, that relate geometry and number theory. Why we call that last theorem? Meaning it's proven at that time, but then it's not proven yet. A little story is Fermat says that this book, the margin of this book is not enough to contain his proof. I mean, yeah. So maybe he's busy. He need to go and flowering his plant. Yeah. So the proof is too easy. So he doesn't write down the proof. But turns out that the machinery we use here is very complicated using geometry. Okay, but this is about last theorem. Okay. Okay, so how about little theorem here? So let's see what little theorem is doing. So let's look at some motivating examples here. All right. So let's say you want to solve 4 factorial mod 5. So basically, what you're gonna do using what we have learned is try write down what is 4 factorial first. Okay, it's just 4 times 3 times 2 times 1. And then mod 5, what does it mean? So you can replace everything mod 5, right? So basically, you can replace 4 by -1, 3 by -2, and then make the smaller number smaller. So you can see that this is just for mod 5 again. Then what do you return? You return -1 mod. Okay. So it seems like the factorial is not doing anything. You return to 4. So let's look at different examples. Let's say 6 factorial mod 7. So what can you do? Maybe you can calculate quicker than me. What do you get? -1 also. Okay, so basically you replace with a smaller number to compute. Okay, so this is the art of congruence. You can reduce number smaller to compute, because you can imagine now in the old days, right, they don't have calculator. Okay, so they will invent a method to help them. So basically you will get -36, which is again -1 mod 7. Okay. So maybe you can try to observe when do we get this mod -1 mod 7. Okay, so what's the relation between 4 and 5? What's the relation between 6 and 7? Okay. Yeah. Okay, but if you try and guess a relation, maybe n and n -1, right? Okay, how about try add factorial mod 9? Okay, try this. Do you get -1 or not? Try and compute. Do you get or not? Do you get? You get 0 instead. Okay, so anything wrong here? Nothing is wrong, but you need to take the right condition to see this. Okay, so what's the right condition then? We will discuss about this right condition. Okay, so what do you do? Okay, so instead, what do you do? So first we have this Wilson theorem saying that if P is a prime, then P -1 factorial is congruent to -1 mod P. Okay, so this is true. I made my note disappear. It might not disappear. Yeah, might not disappear. How come? So let's see. Did I have a proof? Maybe it's easy to see why. Let's show you. Okay. Is it easy to see why? Okay, never mind. So the proof idea of this is basically what we have computed here. Okay. So you group them. You can see that it's quite symmetric. Okay, it's quite symmetry on this calculation here. And then you need to argue why this combination will give you -1. Okay, so this is what you do basically in this proof. Okay, maybe you don't talk about the proof, but the point here is if P is prime, definitely this is true. But the converse is true as well. Okay, so the converse is true, meaning let's say you figure out that P minus 1 factorial congruence to -1 is mod P, then P is have to be prime. Okay, so the converse of Wilson theorem is true as well. So meaning this provide a way for you to prove whether a number is prime or not. Okay, let's say you have a number that you don't know whether it's prime or not, but you know that what's the P minus 1 factorial, and then actually you found out it's -1 more P, then P is prime. So actually what's true is P is prime if and only if P minus 1 factorial congruence to -1. Okay, so this is the fact. This will help us to prove Fermat's little theorem. Okay, we haven't stated Fermat's little theorem yet. Okay, so should we do these examples? Okay, let's do these examples. Okay, so just now I told you something about factorial, right? So how does this help us to compute something in power? Yeah, any idea? Did you see any factorial here? Maybe you can't pull out factorial, but you can cook it out. Maybe. Sorry? Mod -1. Oh, the power is mod -1. How do you bring your mod into your power? So far, later on we will have something looking like that. But for now, not yet. For now, not yet. How does this help? Hmm, 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 hmm. How does this help? Yeah. Any idea? Wait, so let's see. Does it work? So 2 to the 6 is 2 times 2 times 2 times 2 times 2 times 2. Then? Huh? Sorry, you just what? X squared, yeah. And then? So 1 squared. Then you are not using Fermat's. So you are not using the Wilson theorem, right? So can we find out a way to use Wilson theorem? This could be a possible way to do it. Is there a way that you can introduce a factorial into here? Hmm. Yeah. Okay, maybe how about try this? 1 times 2 times 2 times 2 times 3 times 2 4 times 2 5 times 2 6 times 2. Okay, what do you get if I do this? Basically, what I'm considering is like 6 factorial times 2. Okay, so what do you get here? You get 2, 4, 6, 8, 10, and 12. But then, what do you get here actually is 2, 4, 6, 1, 3, 5. Actually, you get a cycle of the remainder of 7 except 0. Okay, is it? Sorry? Yeah, 2 times 6 factorial is 6 factorial here. Huh? Yeah. Okay. So, what do we see here actually? So, mm, so how does this helpful? How is this helpful? We know what is 6 factorial mod 7, right? Just now, what do we know about this? This is minus 1 mod 7. Okay, but we know 2 times 6 factorial mod minus 1, 7. But then, again, on the other side, we have a minus 1, correct or not? Okay, so I multiply minus 1 to both sides. Can I multiply minus 1 both sides? Can I remove minus 1? What is minus 1 here? It's 6, right? 6 and 7, 6, 7. Do you guys is a 6, 7 generation? No. Oh, you guys no. Maybe younger is. Okay, you guys are not. Okay, sorry. Too fashion. Okay, so 6 and 7 have a GCD 1. So that means it is invertible, right? So you can cancel. So you can use cancellation law. So if you use cancellation law, yeah, 6, 7. Okay. So 2 is congruence to 1 mod 7. Wait, is it 2? Hey, what am I doing? 2 to the 6, sorry. 2 to the 6. Okay. 2, 2 equals to 1 is crazy. If 2 is equal to 1, our mathematics can collapse, can drop some already. Yeah. And gulong tika. And you know gulong tika? You guys learn Malay in your MPU? Maybe you can teach your Malay teacher gulong tika. Gulong is like a rolling. What's tika? Tika is like a carpet. Rolling your carpet. When are you rolling your carpet? After picnic, right? For example. So you finish. Gulong tika. Okay. Yeah. Okay. Right. Okay. So do you want to try another question? Yeah. How about I let you try another question using this strategy here? Just try. Let's say, yeah, let's try 2 of these. Let's try B and then try E. Okay. Try this 2. Okay, I give you 4 minutes. See if you can use the Wilson theorem to help you. Okay. So you can notice that all this question here, right, are power to 6. Okay, so it provides a room to apply this Wilson theorem. And you kind of observe that, you should observe that if you do the same, let's say you consider 3 to the 6 times 6 factorial here, you can see that it permute, okay, kind of permute the number 1 to 6 again. Okay. So for example, you will get 3, 6, 9, 12, 15, and 18. Right. So it's commuting 3, 6, 2, 5, 1, 4, which is equals to 6 factorial. Okay. So then this also implies that 3 to the 6 is congruent to 1 mod 7. Very similarly for E, E is E even easier? E actually, are you using Wilson theorem or no? Huh? How is it? How is it? How do you get E? What's the answer you get E? E? Huh? 1 meh? Is it 1? See, yeah. Oh yeah, sure. Yeah. Did anyone of you use Wilson theorem or you use the quicker way? Yes. Anyone try E? Anyone try E? Huh? E? Oh, you also use Wilson theorem? Does it work? It works? Okay, good. But then 6 mod 7 is easy, right? 6 mod 7 is -1, right? Okay, so you just take -1 to power 1. Okay. So this is not a coincidence. Later we'll see why the number get permutes. Okay, later we can see why the number get permutes. But the way I present to you is just kind of a extra method to solve it. Okay? But then I want you to observe this permutation happening. Later we'll see why it is true like that. Why the number get permute when you multiply by the same number. Okay, so from here we can prove Fermat's little theorem, saying that if P is prime and A is a positive integer, such that P doesn't divide A, then A to the P minus 1 modulo 1 congruent to 1 mod P. Okay, so Wilson theorem tells you that P minus 1 factorial is -1 mod P, and then Fermat's last theorem tells you how to solve A to the P minus 1. Okay, when P doesn't divide A and P is a okay, yeah. So this is the solution we get before. So A to the P minus 1, A to the P minus 1 mod P. Okay, P minus 1 is 7 minus 1 is 6, and then 7 doesn't divide 2 to 6. And then it return 1 mod 7. Still remember, 1 is very important in our class because 1 is the identity. They can produce others theorem by others element by just multiplication. Okay. Yeah, so for this, the significance of this theorem is I want you to observe this P prime here, and then the power P minus 1, and then how to return 1. Later, we will review what's going on. For now, just appreciate this formula. And the corollary is we can we can throw away the condition of divisibility. If P is prime, A is positive integer, A to the power P is congruent to A mod P. It's like you multiply A on both sides. Okay, so this is a corollary. It's also true as well. So not that there's slightly different condition here. For Fermat's last theorem, you need P divides A, and then for the corollary, you just need P to be prime. A is a positive integer. That's it. Okay, slightly relaxed condition. Okay, so let's look at this. Let's find the remainder when 4 to the 201 is divided by 11. So remainder remainder means what? You need to find it modulo to some other number. The remainder mod 11. Okay. So can you apply Fermat's theorem or not? Fermat's little theorem here. Sorry. So far cannot, right? Okay, so does Fermat's last theorem work for smaller power? If I want to apply Fermat's theorem here, what does Fermat's theorem say? Fermat's little theorem. What does Fermat's little theorem say? You need A to the P minus 1. Let's see. What's it? What is it? Okay, so A to the P minus 1 congruent to 1 mod P. So in our case, the P should be 11, right? Okay, what's the A here? Is 4. Okay, so we know that 11 doesn't divide 4. Okay, so by Fermat's last theorem, little theorem, we should know that 4 to the 10 is congruent to 1 mod P. Okay? But you are given 4 to the 201. What can you do? You know about 4 to the 10, but you want to know about 4 to the 200. Huh? Can you split it up? 10, right? So you could write 201 as a multiple of 10, right? Yes. Okay, so it's like 20 times 10 plus 12. Okay, so 4 to the 200 is 201 is equals to 4 to the 20 times 10 plus 1. Okay. Which is what? Which is 4 to the 10 power 20 times 4. Okay. But we know that if we mod it by P, which is 11, we can replace this by 1 to the 20 and 4. So in the end, you're left with 4 mod 11. Is that right? Yeah. Okay, so the remainder. So you remember to answer your question, hence the remainder when 4 to the 201 is divided by 11 is 4. Okay. Yeah. So that's why we pick this 401 easier to compute in this case. It's a multiple of 10 plus 1. Okay, so far so good. So far so good. Okay. Yeah. So this is another way to get number 1. Okay, using Fermat's little theorem. Okay, so next part we're gonna explain what's the significance of that P minus 1. Why P minus 1 works? Okay, why does P minus 1 works here? Okay. Is this example important? Let me see. I guess this example is not very important. It's similar to what we did already. Okay, so let's skip it. So you can try and do it. In fact, I set a new question to this. Actually, you can do 2026 to 2026. You can try 2023 as well. Okay, but then let's continue. So we're gonna define a new function here. Okay, call the Euler phi function. Phi n is defined to be the number of positive integers not exceeding n that are relatively prime to n. Hey, have we seen this kind of function before? pi x. What's pi x? Do you still remember we introduced a function called pi x last time? Or number of prime numbers. Okay, so this one is a number of positive integer that are relatively prime. Okay, previously are all the prime numbers, but now are relatively primes. Okay, so a bit different, no? So let's try what do we get for different n. So let's try for n from 1 to 12 here. So let's figure out what is phi n. Okay. Let's do it together. And then all the numbers such that GCD of AN is 1. And then this number cannot exceed n. And then phi n is just counting how many of them. Okay. So how many number that's strictly less than 1, the GCD is 1. Not exceeding, right? Could be equal, right? Yes. Not exceeding. Could be equal. Okay. So, well, what number is GCD 1 with 1? That's less than 1. Equal to 1. And then this A has to be positive. If it's not positive, it could be -1, right? So we just take 1. Okay. We don't take -1 because we have to be positive. Otherwise, you can have a version that includes -1. Then how about 2? There are only 2 things you need to consider, right? 1 and 2. Okay, but 2 has GCD 2 with 2, so only have 1. So how many of them? 1 of them. Okay, and then how about 3? 1 and 2. 3 have GCD 3 with 3. Okay, so it's not 1. So there are 2 of them. 4, 1, 3, and no more. 4 has GCD 4, 2 have GCD 2 with 4. Again, 2, 5, 1, 2, 3, 4, 5. No 5. Because GCD 5 and 5 is 6, 1 and 5. Okay, because 2 and 3 have GCD 2 and 3 as well. Yeah. 4. What's the GCD between 4 and 6? Is 2, not 1. Okay. So here's 2. About 7. 1, 2, 3, 4, 5, 6. Okay. And then should we continue? Maybe we can stop here. Okay. So what did you observe here? When it is prime, it's easy to compute. Why? Just everything before it. How many of them? P minus 1. Okay, this is the power that occur at the Fermat's little theorem. Okay, P minus 1. Okay, for the rest, then you need to figure out how many of them. Yeah. Right. Cool. Okay, so later we'll prove a more general version of Fermat's little theorem based on this function. Okay, so next we will introduce something called the reduced residual system. So a reduced residual system modulo n. So previously you have the complete residual theorem, right? System. Basically, you just pick all the remainder, okay, as your system. But now the reduced one means what? So you pick number such that it is relatively prime to n. Okay, so you just pick those are relatively prime to n. So meaning, these are the reduced. So here, this part is the reduced residual system. Okay, and there are 5 n of them. Okay, so there are 5 n of them. Okay, such that each element of the set is relatively prime to n, and then none of the 2 is the same. Does it make sense? Okay. Okay, so how about give reduce system modulo n to 1? Okay, so there are only one choice, right? So number one here. Okay. Can I pick -1? Can I pick -1? Such a evil. I think I can pick -1 as well. Because I only care about integers, right? Okay. But then I cannot pick 1 and -1. I cannot pick this. Can I pick this? I only have R phi n of them, but phi n is 1, phi 1 is 1, right? Okay. But then why we cannot do this? Because 1 and -1 is the same mod 1. Okay, so we need to make sure they are not the same. Okay. Make sense? In fact, I can choose another one. I can choose 0. Because 1 is 0 mod 1. Okay? Does it make sense? So in this world, mod 1 world, 0 and 1 is the same. Correct or not? You mod 1, right? Mod 2, 2 becomes 0. Mod 3, 3 becomes 0. Mod 1, 1 becomes 0. Okay, 1 and 0 is the same. Okay. So how about 2? What sort of reduced residue theorem system you can pick? What is 5-2? 5-2 is 1, right? Okay, so you can only choose one thing inside there. Maybe you can pick 1. Okay. Does it make sense? Makes sense. I mean, I think you are a bit confused. So reduced residue theorem, maybe I repeat again, is a set of number, phi n of them, phi n integers, such that each element of the set is relatively prime to n. So meaning you need to find a set of number that's relatively prime to n. Okay, this is basically what we are computing just now. Okay. But then my point here is you can pick a different system. Okay, pick a different representative. What I said last time. Okay, so how about you give me, maybe you try. How about number 3? What is phi 3 that we figured out just now? Maybe go back to this table. What is phi 3? 2, right? Okay, so you should choose 2 number that's relatively prime to 3, but then they are not congruent to each other. Can you pick the 2 number here? We are kind of like backward doing stuff. About 3. What number can you pick? Relatively prime to 3. Sorry, 1 and 2. Okay, 1 and 2. Okay. And how about 4? 1 and 3. Okay, good. And then 5? 1 and 2 and 3 and 4. Okay. And then 6? 1, 5. Good. Okay, and so on. Is people okay? Or you want to try one more exercise? Want to try one more? Maybe try number 12. The largest one in the list. What are the numbers that's relatively prime before 12? 12. 1, 5, 7, 11. Yeah. Okay. And then note that 5, 12 is 4. Okay, it's enough. Okay, none of these are the same. Okay, none of these two are the same. Okay, does it make sense? Okay, yeah. But then you cannot choose something like this. You cannot choose like 1, 5, 17, right? 11, like that. You cannot pick this, okay, because 5 is congruent to 17 mod 12. Okay, you need to make sure that all of them are different from each other. Okay, does it make sense? So that you can fully fill your 5 n numbers of them. Okay, good. So another theorem is if you have a reduced residue system and A is a number that's relatively prime to n, then A multiplied to this Ri, right, is also a reduced residue system. Okay, so this multiplication will preserve the relatively prime property. Does it make sense? So but you cannot multiply with anything, any numbers. This number that you multiply has to be relatively prime to n first. Does it make sense? Okay, this will answer what we had just now. Okay, so if you look carefully on this calculation, right? This calculation here. Okay, how about this calculation? So what you see is you multiply 3 to 1, 2, 3, 4, 5, 6. Okay, but 1, 2, 3, 4, 5, 6 are relatively prime to 7. Does it make sense? So that's why it permutes the number 1 to 6, because it stays as a reduced residue system. Reduced residue system must have 7 of them. 5, 7 is 6. Does it make sense? And 3 and GCD of 3 and 7 is 1. Okay, so that's why you have this permutation coming out. Does it make sense? Make sense? Okay, yeah, okay. Okay, so yeah, okay, let's continue. Then we have this Euler theorem. Okay, so generalizing the Fermat's little theorem is, instead of putting p minus 1 there, I will put 5m. In this case here, I don't require my m to be prime anymore, because phi of prime is always p minus 1. So this is more general. Okay, if I want to take a to the 5m is congruent to 1 mod m. Okay, so the secret of Fermat's little theorem is the p minus 1 represent the number of integer that is relatively prime to p. Okay, so this is more general. Does it make sense? Okay. Okay, so the p minus 1 is not mysterious. It's not a mystery. Okay, it is actually counting how many number that's relatively prime to p. Okay, so if you forgot Fermat's little theorem, this is enough for you to recover Fermat's little theorem. Any question? Any question? So I'll say here, if if m is prime, then 5m is just m minus 1. Okay. So Euler's theorem will specializes to Fermat's little theorem. Okay, so from here, actually, you can realize that actually Euler's born later than Fermat's. Yeah, I think so. And Fermat is not a full-time mathematician. Fermat is a judge. He's a judge. Yeah, he do law. You know law? Yeah. So when he do mathematics in his free time. He take a book, a bunch of questions and solve it in his free time. I also got a friend studying when I back in Australia, right? We have double degree. I also got a friend doing degree of law and degree of math together. Took like 5 years to finish. Yeah, kind of long. Double degree. Law in mathematics. Law and mathematics are quite different, although they are similar in the sense that they need logic step by step. But then law, you could have a different interpretation actually. You can manipulate somehow. But mathematics is relatively hard, or actually you cannot manipulate once the definition is given. But then the nice thing about mathematics is we can create weird or exotic definition that can work for different environment. Okay. Yeah. Actually, we have one more exercise less. Maybe we can leave it for next time. Yeah. Maybe you can stop here, Euler's theorem. Okay, see you. If no question, we'll see you on Wednesday. Yes. OK， 你是谁人？哦，王野，王野的话，哦，你是什么号码？你是什么 DMP？
啊，对对对，
那个这个。哎，哦 ，OK， 好，谢谢。哎，你要点名？
我点2次了，
那你点2次？
我不知道是不是有人名字我很像。
哦，对对对，看。
我想问一下，我们有3门对吗？然后我们是要去 explain 那些solution 跟 explanation 要完全跟你教的一样吗？
比较好啦，比较好。对对对，不然的话，等一下有时候我不知道你知不知道。